See that now online, right? I'm not imagining things. Okay. Okay, so today I just want to talk about worksheet number 4 and going over that stuff so that we can see if we can do Planet Newtonia from home tomorrow. What do you guys think of this? Was it okay? Is it starting to feel a little bit better? I'm trying to figure out how we can work a lab in. That's not going to make us all crazy. Okay, so let's see. Where on the graph above is the object moving most slowly, and how do you know? So what we want to know here is where our velocity is 0, right? That would be our slowest. And the way that we could do that is we could find the locations where the slope of the line is horizontal. So where the slope is horizontal is where velocity equals 0 meters per second. So if we take our slopometer, the first place that it happens is B, and then the second place that it happens is F. So this should be B and F. Next, between what points is the object speeding up? So if we're looking for speeding up, we're looking at a slope that gets steeper. Right? And so our fastest points are going to be where our slope is the steepest. So if we look what's happening from A to B is it's slowing down. From B to C, it speeds up, and then it maintains its velocity through E. So I would say from B to C is the first one. And then we're our lowest again at F, and then from F to G, it speeds up. So there's 2 places where that slope gets steeper. You guys have any questions about that one? Okay. Between which points is the object slowing down? So this is where the slope gets more horizontal. I don't know. Is that the easiest way to say that? I'm not sure if there's a mathier term. Maybe more level. I don't know. I think horizontal is clearer. So it gets more horizontal. The places where that's happening, like we said a minute ago, is where we're going from A to B. A to B. And then it flattens out between E and F. So we start kind of steep, and then we get flatter. So E to F. How are we doing so far? Good? Yeah, you guys are getting this. So where on the graph is the object changing direction? So this one's tricky. So remember, the sign of the slope tells us what direction it's going. So we want to look and see where, let's see. I mean, that might be the easiest way to say it. Where the sign of the slope changes. For a motion like this, that's going to be near where it becomes 0 because we have a positive direction here at the beginning. And then from B to F, we have a negative direction. So one place it's going to change direction is B. The other place it's going to change direction is if we're moving in the negative direction, because our slope is negative, through F, and then our object starts to move in the positive direction, that's another turning point. So it's going to be B and F. So for this data set, it happens to be the same as where our object is moving the most slowly. What questions do you guys have about page 1? Anything? Concerns? No? You guys feel okay about that one? All right. Okay, second part. And we set some of this stuff up a little bit a couple of days ago. So there's some data here. First thing says, give a written description of the motion. Well, we know that our object starts at 25 meters. It's going to move, you could say either in the negative direction or towards 0 meters. Either of those is okay. And can we say anything about the velocity? Is the velocity constant? The velocity is not constant. We've got an arc here. So we don't have a constant slope. We have a changing slope. So we know that it's accelerating. This is represent object B's motion. So this is object B. It says up on our graph, object B. Represent object B's motion with a motion map. Include both velocity and acceleration vectors. So I could actually figure out some of these, right? If I wanted to do this with each second, I've got a dot there, dot there, dot there, dot there. Do you guys take the time to do that? So if I wanted to draw those dots, I would probably, I don't know. Did you guys just stick to the little line? Yeah. Okay. So 1, 2, 3, 4. If I'm going to say like this one here is 25, 20, 15, 10, 5, 0. So my first dot is going to be pretty close to 25. My next one is also going to be close to 25. Then 24. Oh, this isn't really to scale already. Next one. 20. Almost 15. Do you guys see how these are spreading out? I think it's cool. 10, 5, 0. Okay, that's how I drew my dots. Did you guys get close to that? They're close together, farther away, and then they get farther apart as you get closer. And I'm going to switch colors. This looks festive. Okay. So I'm going to have tiny arrows, and this is supposed to give me an idea about my velocity. And so what we should see is that if our velocity is increasing in the negative direction, our arrow should get longer, pointed towards 0, which seems to be what they're doing, even though my motion map seems to be a little bit squished. For my acceleration arrows, I'm going to draw my dots in the same place because my dots tell me about position and nothing else. All right, and as we can see that these get a little bit longer pointing to the left as we go on, we can say, okay, well, if the change that's happening to velocity is that it's increasing that direction, then I can make small arrows that are all about the same size because this is our constant velocity unit, or sorry, our constant acceleration unit. And so if we're going to have acceleration, it's going to be constant. So I'm just going to try to draw arrows that are very similarly sized. Am I going to be perfect at this? Probably not, but it's just qualitative. It's not really a quantitative map. So for velocity, I should have arrows that get longer. For acceleration, they should all be about the same length, and they should all be pointing in the negative direction. Any questions so far? How do you guys feel about motion maps at this point? Nah. Okay. I'll take it. We'll be pros by the end of the year. All right, next, the displacement from 2 seconds to 8 seconds. So now I have to figure out what my position was at each of those. So if I look up at my graph, it looks like I've got 0, 1, 2 seconds. This looks like 2 seconds and 24 meters. And then 6, 7, 8. This one down here is 8 seconds and 9 meters. Do you guys get those? So our displacement, our final position is going to be 9 meters, and we're going to subtract from that 24 meters, and that's going to give us minus 15 meters of displacement. So it's telling us we went 15 meters in the negative direction. Next, to find the average velocity, we're going to take our displacement that we just calculated, so our minus 15 meters, and divide that by our change in time. 8 seconds minus 2 seconds is 6 seconds. So I'm going to grab my calculator because it's not exactly even. I think it's 2.5. It's 2.5? I think it's 2.5. So minus 15 divided by 2. Why did I do divided by 2? Divided by 6. Yep. So I got minus 2.5. And the units for that are going to be the same as the units that we used in the calculation. So it's going to be minus 2.5 meters per second. That's our average velocity. Next, instantaneous velocity at 2 and 8 seconds by finding the slopes of tangents. So we're going to have to draw some pictures here. So you remember when we did that very first thing in the packet, we were trying to find the instantaneous velocity of the midpoint. And we did that by looking at the average velocity of 2 points that were an equal amount of time on either side. So the way we're going to find the instantaneous velocities at those points is by looking at our data table up here. And I'll tell you what, you guys see how the 3-second one isn't exactly on a line, but the 4-second one is? For number 2, I actually personally, I like to choose the 0 seconds and the 4 seconds. And that line should be the same slope as it. Look at me, I didn't even draw my tangent right. It should be the same slope as at 2 seconds. And then for 8 seconds, when I look at it, the 9 isn't quite on there, and neither is a 7. But if I pick the 6-second and the 10-second, it's a lot better. So I'm going to pick those two. It's okay if you pick those two. You can do that, and that will work just fine. But those are the ones that I like to choose. So for my 2-second instantaneous velocity, I'm going to do my change in position for 4 seconds and 0 seconds. So my final position is 21. And I'm going to subtract from that 25 divided by, and the difference between these is 1, 2, 3, 4 seconds. So I've got minus 4 meters divided by 4 seconds is minus 1 meter per second, which is much lower than this one, right? So maybe the next one is going to be higher, so that this is the average, because this is the average between the two. So if this one's lower, this one should be higher. You can actually guess how much higher it should be, by the way. It's probably 4, right? Because the difference here is 1.5, so I should be 1.5 higher than that. Okay, so at 10 seconds, I'm at 0 meters, and I'm going to subtract from that my position at 6 seconds, which is 16 meters, divided by 1, 2, 3, 4 seconds. So I've got minus 16 meters divided by 4 seconds equals minus 4 meters per second. So in fact, if you take these two things and average them together, 4 plus 1 is 5, divided by 2 is 2.5. So that's just another way you can confirm that. To determine the average acceleration from 2 to 8 seconds, we're going to look at our two velocities. This is why we just calculated them up here. Here, our velocity at 8 seconds is minus 4 meters per second. So you got minus 4 meters per second minus 1 meter per second divided by the change in time between the two, which is 6 seconds, right? 8 minus 2. So this is going to be 4 minus 1. That's going to give us 3, right? So this is 3 meters per second. Sorry, minus 3 meters per second divided by 6 is going to give us minus 0.5. And the units here are meters per second divided by seconds, which is the same as meters per second squared. You guys need to see how to go from meters per second divided by seconds to meters per second squared. How many of you guys feel good about how to do that? How many feel not good? Okay. So if you guys have questions about this jump later with the units, just let me know. All right, what's the instantaneous velocity at 5 seconds? And then explain. So here's the thing. If you realize that 5 is in between 2 and 8, then you know that the average velocity between 2 and 8 is your instantaneous velocity at 5, which means we don't have to calculate anything because we already did that. So our instantaneous velocity is equal to our average velocity at 5 seconds. So that average velocity is minus 2.5 meters per second, and that's from part D. Okay, what questions do you guys have about the first page? Any questions? No questions. Okay. Next part. Yeah. Okay, next one. So we're given a graph, and this is velocity versus time. So this is how fast our object is moving across the time of an experiment or a measurement. So when we're looking at a written description of the motion, we can't really say where the object starts. All we can say is that the object is moving in a negative direction because it has a negative velocity. We can also say that it moves for 8 seconds, right? Because this would be 8. We can also say how far it went. How do you guys feel about that one? So do you notice there's, let's see, each one of these squares is 3 meters per second times 1 second. So each box represents 3 meters of travel. So if I count my boxes, if I count the ones that don't have a line in them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then if I look at these down here, can you guys see that this space here is the same as this space here? And that this space is the same as this one? So this is 2 boxes worth, and then this one is 2 boxes worth, so that's another 4. So if we've got 12 plus 4, that's 16 boxes, 3 meters each, and we know that it travels for 48 meters. It's not, I mean, it's quick, right? We can do that. We can also say that this object, because it has a changing velocity, that it accelerates. So I'm going to say it accelerates in the negative direction. I think that's about all that I can say about the motion. Did anybody have something else that they wanted to add to that? No. Okay. So next, a motion map. So with our motion map, we're not really told where it's started, but it is moving in the negative direction. So we know we're going to start down at this end. And we know that our velocity is going to get more negative as time goes on. So that arrow should get longer. So I'm going to start these, it's got to spread out with each dot. So you have to kind of start them close together so that you can separate them and have more than 1 or 2 dots, but you don't want to start them so close together that you end up with a ton of dots. There we go. I'm going to go with it. What do you guys think? I like the thumbs up. That's good. Okay, so I'm going to recopy my dots so I can draw my acceleration. And I've got a line here for my velocity that is constant and negative. So I'm going to have a constant negative acceleration. So all my arrows for acceleration should be similarly sized and all pointing in the negative direction. Again, we could calculate a number for that, but we haven't, so we're just going to make these qualitative. All right, next we have some math to do. This thing about displacement, we can do this by looking at the area between line and the that velocity versus 0 axis thing right here. So between 0 and 4 seconds, what we want to know is the area. I'm going to sketch it in all pink. We kind of alluded to this already. That pink section there is going to be, we can calculate this like a trapezoid. You guys know the equation for a trapezoid? I know, right? It's something like this height plus this height divided by 2 divided by times the length, right? I just think about it as trying to figure out what the area is. So if we can find the area, then we know what the displacement is. So displacement equals area. So to figure out the area here, like we said before, each of these boxes is 3 meters because each one is 3 meters per second times 1 second. So let's see, each box. So each box is 3 meters. If I count the number of boxes, I've got 1, 2, 3, 4. And then this one plus this one gives me 5. This plus this gives me 6. So this is a total of 18 meters. All right, so that's one way to do it. The other mathier way to do it would be to look at, and it should be, by the way, negative. The other way to do it would be to take -3, because that's the height of the short one here. So -3 meters per second plus -6 meters per second divided by 2 times the amount of time times 4 seconds. So this is something like, I could say velocity 1 plus velocity 2 divided by 2 times time is the other way to find this displacement. So that's what this looks like filled in. It's the height of one side of that trapezoid plus the height of the other divided by, the height of one plus the height of the other divided by 2, which is basically going to give us this value right here in the middle. So that should be 4.5 times 4. So if we've got 4.5 meters per second times 4, what are we going to get? 4 times 4 is 16. 0.5 times 4 is 2. 16 plus 2 is 18. That's negative, so -18 meters. So we end up with the same value both ways. Which way do you guys like better, the graph way or the equation way? The equation way? No. Some people like both. So you can use either one that you want. Both of them should work. The next step says determine the displacement from 4 to 8 seconds. So here, 4 to 8 is going to be the second part. So that's this part. So we can either do count the boxes, which is going to be, which is going to be 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10. 10 times 3 is 30 meters. So minus 30 meters by counting boxes. Or we can make it mathier and do it the mathy way, which would be, sorry, I don't like to scooch back and forth. I'm trying to get it all in one shot here. Okay, so if we're looking at the height of the first part, that's going to be -6 meters per second, plus the height at the end, which is going to be -9 meters per second divided by 2, times the time that passes, which is 4 seconds. So -6 plus -9 is going to give us -15 divided by 2 is -7.5 meters per second. So that's our average velocity through that time period. So it's the same as looking at what the velocity is right in the middle. Times 4 seconds. 7 times 4 is 28. 0.5 times 4 is 2. 28 plus 2 is -30. So we get the same answer. Any questions so far? How'd you guys do? Did you guys do okay on those? Okay, a lot of you guys are shaking your heads yes. All right, determine the average acceleration of the object's motion. So to do that, we need to know the change in velocity divided by the change in time. And we've got a perfect graph for that because we can see that at the end of our motion, we're at -9 meters per second. At the beginning, we're at -3. So we're going to take our final, -9, minus our initial, -3. Forgot my units. And the entire amount of time there is 8 seconds. So -9 minus -3 is going to give us -6 meters per second as our average, divided by 8 seconds, which is going to be minus 0.75 meters per second squared. And then the trickiest part, sketch a possible position versus time graph for the motion of the object. Alrighty, here we go. Explain why your graph is only one of many possible graphs. Well, the thing about our original data is that it doesn't tell us where the object started. So the reason that what we're going to draw is one of many possible graphs is because you could start anywhere on this axis. You could start down here at the bottom, you could start at the top, any of those would be okay. So we've got an object here that starts with a negative velocity, and then the negative velocity gets bigger. So if we just play with our slopometer, if this is a 0, this is a negative velocity, but our object is going to get faster and faster, so that slope is going to increase. And so what that means is when we go to draw our line, it's going to look something like, it's not going to start flat because we don't start with a zero velocity. Like zero velocity is somewhere over here in the past. So we're actually going to start with kind of a negative, and it's going to go down. So all you have to do to get this question right is have that curve. It can start at a positive position. You could start it at, you could start it here. You could start it here. Any of those would be correct. All right, what questions do you guys have about object C? Any questions? Okay. Object D. Object D is trickier because our graphic does a little dog leg thing, right? So when our object starts, again, this is a velocity versus time graph. It doesn't tell us where our object starts. But we do know that the first 2 seconds, I'm going to write 0 to 2 seconds, our object has a constant velocity. Do you guys see that? It's kind of tricky to go from looking mostly at position versus time graphs to velocity versus time graphs, because the common mistake would be to look at this and say that our object isn't moving. But that's not what this says. What it says is that our object has a constant velocity. The place where our object isn't moving is here. There's a very brief moment where our velocity is 0. That's where our object is not moving. That's also the point where we switch from having a negative velocity to a positive velocity. So that's a point where our object turns around. So from 2 to 4 seconds, I have a decreasing velocity or decreasing speed, but still in the negative direction. I'm going to say at 4 seconds, my object turns around. And then from 4 to 8 seconds, object has, you can either say it accelerates in the positive direction or it has an increasing speed in the positive direction. All right, motion maps. So to draw our motion map, we're going to start our object, and I know that it's going to go in the negative direction first, and then the positive direction. So my object is going to start someplace, go negative, and then turn around and go in the positive direction. That turnaround is going to happen at 4 seconds. So my first 1, 2 dots for my initial one are going to be equally distant. So I'm just going to try to draw this. I'm going to start here, and that'll get me from 0, 1 to 2 seconds. 0, 1, 2. At 2 seconds, my object starts to slow down for the next 2 seconds. So I'm going to get my dots a little bit closer together. I'm going to put my next one down there. It's my turnaround dot. 3, 4. And then after 4, I'm going to increase in velocity each second. So my next second, I travel 2 meters. It's actually going to be half that, right? So I'm going to go 2 meters. And then the next second, I travel 4 meters. And then the second after that, I travel 6 meters. Let's see, half, 1.5, 2. So it should be something like that. So I actually end up farther away than I started. For my arrows, I'm going to draw my arrows halfway between the dots. Slows down and then speeds up. I'm going to copy my dots so I can do acceleration. So remember, acceleration is only where my velocity is changing. So we know that our velocity does not change here at the beginning. So I'm not going to draw any arrows at the beginning. None. So here's 0, 1. They don't get any arrows. This one, Do you guys see all the way across this, no matter if the velocity is positive or negative, the acceleration, the slope of that line is always positive, which means your acceleration arrow should always point in the positive direction here. And that happens after 2 seconds. So I have 0, 1, 2, and then my arrows are going to point to the right. Oops. And they should be all about the same size. This is the one where it kind of throws people because it looks weird to have it there. But one way you can think about it is that the motion is going this way, and then something is going to push it back that way. Mara. Of Sydney. Yeah, of course. So a way to think about this is I've got an object that's moving in the negative direction, and then where this pink arrow starts, that's where something is going to push it back and make it go the other way. Okay, do some numbers. Determine the displacement from 0 to 4 seconds. This is the whole portion at the beginning. All this stuff. So, it's a little bit complicated, so we're going to have to think about this for a minute. If we want to do it by counting blocks, each of these blocks is 1 second long and 2 meters per second high. So each of these is worth 2 meters. So if I just count the blocks, 1, 2, 1, 2, 3, 4, 5, and then these two together make 6, I should have 12 meters. So if I count the blocks, 6 blocks times 2 meters per block equals 12 meters. If we want to make it mathier, if you like doing your area calculations, I would do this as 2 parts. I would do it as the first 2 seconds and then the last 2 seconds. The first 2 seconds are going to be 2 seconds times minus 4 meters per second. And this is just velocity times time. And we're going to have to add to that what's going on with the second part. So with the second part, we're going to have, we need to find our average velocity. The average velocity there is going to be minus, let's see, make it 0 plus minus 4 meters per second divided by 2 times 2 seconds. So here our first part is going to be minus 8 meters. The second part is going to be minus 2 meters per second times 2, which is going to be minus 4 meters. So that's going to get us to minus 12. Same as up here. So it's 2 different ways that you can solve it. Next is determine the displacement from 4 to 8 seconds. I think this one's a little bit easier. I don't know about you guys. But this is going to be the portion that's where our object is moving in the positive direction. If we want to do it by counting blocks, this is going to be 1, 2, 3, 4, 5, 6, and then 7, 8 blocks. So we've got 8 blocks times 2 meters per block is 16 meters. The other way that we could do it is with math. So to figure out the area of this triangle, we're going to do half times the base. So 1/2 times the, sorry. I actually think about this as 1/2 the height, but we could do it. You guys like 1/2 base times height? Does that just make it easier for you? Okay. So the reason that works is because it's finding the average height. It's finding the average velocity times the time. So it's not actually half times the time. So half times the base is going to give us, the base is 1, 2, 3, 4 long. So 4 seconds times our height here, which is 8 meters per second. So 1/2 times 4 is 2, times 8 is 16. So we get the same value as by counting the blocks. Next one is trickier. Determine the displacement from 2 to 6 seconds. All right, guys, 2 to 6 seconds is this. What do you guys notice about the area on both sides? Is the number of blocks the same? But one is positive and one is negative? So what's the total going to be? What's our total displacement going to be then? What do you guys think? Well, we can figure out what this piece is we already calculated it down here, right? We said that piece was, where'd it go? Was our 4 meters. So from 2 to 4 is 4 meters of displacement. And then from 4 to 6, we can figure that out if we do 1/2 base times height. So half of the base would be 1 second times the height, which is 4. So that's 4 seconds. So from 4 to 6 is going to be plus 4 meters. So our total is going to be minus 4 meters plus 4 meters equals 0 meters. So from 2 to 6 seconds, there's been 0 displacement. Our object traveled some distance, right? Our object actually traveled 8 meters, but the displacement, the change in position between that time and between 2 seconds and 6 seconds is going to be 0, because when you add those two distances together, you end up back at the place where you started from. So when we look at our motion map, we ought to be able to look at this and say, okay, 0, 1, 2, 3, 4, 5, 6. So if I had drawn this accurately, those two things would line up with each other. Does that seem plausible? Dr. O'Malley made enough error on the motion map that it doesn't line up. Yeah. So if I had been paying more attention, I could have been more careful about that and lined it up correctly. So the point there is that the displacement is 0, even though our object has traveled some distance. Next, it says determine the object's acceleration at 4 seconds. All we need to do here is figure out the slope. And because our slope is constant across here, this should be something that's pretty straightforward to do. I don't like to mess with negatives because I get myself in trouble sometimes. I don't know if you guys are the same way. So you can figure out the slope just by using the positive parts of the graph because the slope up here is the same as the slope down here. So if I start from 4 to 8 seconds, I can figure out my slope by looking at, see, I'm going to do my change in velocity divided by my change in time. My final velocity here is 8. I'm going to do 8 minus 0 meters per second divided by 8 seconds minus 4 seconds. So at 8 meters per second divided by 4 seconds gives me 2 meters per second squared. Oh, sorry, I need to scoot that up. So if I'm looking at just the data there for my from 4 to 8 seconds, that's reflected down here with the time, I'm going to subtract my final position and my final time. Sorry, from my final position, final time, the initial position and time for that point. So I'm going to do 8 meters per second minus 0 meters per second divided by 8 seconds minus 4 seconds. I got 8 meters per second divided by 4 seconds for 2 meters per second. And you should have gotten the same value no matter where along this line you chose your points. Did everybody get 2 meters per second squared? Cool. All right, last. This one's the hardest question on this whole worksheet. How do you draw this thing? Right, because it changes. We've got a change in direction. We've got a constant velocity and then a positive accelerate. It's kind of a mess. So for this first part, the first 2 seconds, we have an object that's moving at a constant negative velocity. So I'm just gonna, because it's kind of going negative, and I know it swings positive, I'm gonna start down towards the bottom. Drew my little hash marks there. So I'm gonna start by having I'm gonna have a negative velocity. There we go. It doesn't matter where you pick your starting point. We're just looking at shapes here. And then my object is going to continue to have a negative velocity, but it's going to get closer to 0. So my line, if I use my slopometer, should start out kind of like this, and then it's going to flatten out because it's approaching 0. As it gets closer to 0, my slopometer here is going to get more and more horizontal. So I reach 0 at 4 seconds. So I can actually, if I'm lining these up, there's 2 seconds. Here's 4 seconds. So that's where it should bottom out. So I'm going to draw that like that. So there's where I slow down and turn around. And then after that, I'm going to gradually increase my velocity. So I'm going to start at 0 and I'm going to increase my slope until I get to the highest point at 8 seconds. So I'm going to start feel like I can't draw curves when my paper is oriented in some ways. So I'm going to start with it kind of flat and then make it steeper and steeper and steeper and steeper. So it should look something like a not quite symmetric bottom of a pond or something. How'd you guys do on that one? That one's tricky. Did okay? Okay, so I'm going to give you guys some instructions about tomorrow. So I don't anticipate being online myself tomorrow for your classes. I need to take my son to an appointment. But you guys are going to work on Freefall and Planet Newtonia. Does everybody have a ruler at home? Okay, you need a ruler for this. So if you need to borrow one, let me know and I'll lend you one. But what you're going to do is you're going to collect some data. Your data is for this page. So if you flip one page over, you have a dot here. And what's going to happen is this dot represents an object that's falling on planet Newtonia. Just go with it. It's fun. You're going to collect some data. What I would recommend is that you choose something to be 0. If you like working with positive numbers, you might want to choose down here to be your 0 line instead of up here, because then you can measure upwards and say, okay, this was at this location, this is this. And then you'll be working with positive numbers. If you start with A being 0 and measure downward from A, then you're going to be working with negative numbers the whole time. It works either way. So you can do it either direction. But my recommendation is make E 0, because then you only have to deal with positive numbers and you don't have to spend time worrying about that. Then what you're going to do is collect some data, and using your data, answer the questions on this page. Just make sure that you use the space to describe what you were doing and what equations you were using. And then our plan will be that'll be due on Thursday, and we'll go over it on Thursday. You guys have any questions about that? No.